Hi learners, in this session let us have a look at what a Turing machine is and how is it advantageous over push-down automata and finite automata. Before proceeding to a clear understanding on Turing machine, let's have a look at what a finite automata is. Finite automata is just an automation model that can understand a pattern of a language. So it could be defined by using 5 tuple q sigma delta q naught and then f. So q the set of state, sigma the set of input symbols, delta is the transition function, q naught is the start state and f refers to the set of final states. The drawback or the limitation of finite automata is that it doesn't have a memory element associated, and hence finite automata plus the memory element, which we call as stack, called as pushdown automata. This pushdown automata again is represented using a 7 tuple including the finite automata along with two more components. One is tau representing the set of stack symbol, another is z0 which is used to refer to the bottom of the stack. So the memory element that is used here is stack, or which is operating on last in first out basis. So you will have a memory unit wherein you can push and you can pop it out. Always the element which is on the top will be available to the user. So the limitation here is that it permits only unidirectional movement, and hence not all the languages could not be recognized using pushdown automata. Let us see one sample language wherein, let's say, if the language is a power n, b power m, c power n, d power m. Right. So we do have only one stack. If it is multi-stack, fine. I can insert A onto one stack and B onto another stack and I can check. But if there exists only one stack, which is there is the basic concept of pushdown automata. So if we insert A's onto the stack and then if we push B's onto the stack, only B's will be available for testing, not the A's. Okay, but here in this language, C's to be equated to A's and B's to be equated to D's. So this kind of languages is not possible to be designed using pushdown automata. So the concern here is, so whenever there exists a concentric circle in the type of languages that you have, let us say a power n, b power m, c power m, d power n. So if you could map like this concentric pattern, or if it is a power n, b power n, c power m, d power m, where you have like this and like this, you can go for using pushdown automata. Languages of this kind is definitely not possible. And hence we move on for the next evolution of your programming model, which is Turing machine. A great credit to Alan Turing, who has introduced this concept of Turing machine, which is behaving as the base model for all the computational devices that we do have today. So in this video, let us have a look at what a Turing machine is and how is it advantageous over pushdown automata in both recognition as well as execution. And then let us see what kind of languages could be accepted by this Turing machine. Let's move on. All of you would have seen these kind of buttons, right? What a finite automata will do, you will have a state diagram wherein you can start from a particular state. You can keep on reading the symbols, okay? And then when you want to stop at a particular point, you can press this pause button. When you reach the final state, then we say we have come to the end of the session or the traversal. So these buttons are used to move across the different finite automatas that you do have. So just this is a mapping to the state conditions of your finite automata. Moving on to pushdown automata, which is the next evolution in line of finite automata. Now that you have access symbols, the finite automata remains same. Along with that, now assume you want to retain states of multiple players. Okay, so this finite automata is used when you have a single player system. So if there exists a one player game, okay, where you don't need to memorize any state, okay, no state remembrance. You open a game, okay, you play, and when you close, automatically the state of the system will get loosened, okay. After that, when you come, it will be a new game. Not you cannot retrieve back or restore the state of the system. That's what a finite automata means. But in most of the cases in current generation, we are expecting the system to remember the state of where we have left. Okay. For example, in a two-player game, if player one plays and then player two plays the same game, okay, and if the player one goes in pass for some time, and if the player two is playing, okay, the state of this player one has to be remembered so that it can be restored when he come back. Similarly, the state of this player has also to be remembered when he comes back. That's where we are in need of your memory element. Moving on, this is the limitation already we have explained. So there is only one side traversal in pushdown automata, and hence if you want the machine to accept these kind of languages, it is not definitely possible. And hence we move on for Turing machine. Turing machine, just before getting in detail or in technical detail of it, just let's have a look at this. All of this we could have seen in our earlier days or young age. Okay, nowadays most of the people are not using it. This is a cassette which we can insert into a tape recorder. So this cassette will have a tape. Okay, so this tape is where you can record all your data. So this tape is a continuous strip. Okay, here it is finite because the size of the box is finite, but logically it's an infinite tape where you can have cells. In each and every cell, you can store a single element. Okay, so let's say 1, A, yes, a space, blank symbol or anything. Initially, when this cassette is being bought, it will be filled as only blank symbol. The tape will be empty. As and when you try to record some song, automatically this cells will be filled up with data. Okay, so this when you try to record some data, automatically the tape will get wound from here to this particular thing. So when you want to revise or rewind, the tape will get wounded from this particular area to this particular knob. So that's the functionality of cassette. This tape as such won't be of use. This tape, which acts as a memory unit, has to be inserted onto a player of this type, which we call it as tape recorder. So this accessing unit should have some control buttons of this kind. Let's say you should have a play button to start working. Then if you are in need to stop for a while, you need to have a pause button. When you reach the final state, we should have a stop button. And we do have two more buttons here. One we call it as forward, another one we call it as rewind. So what these buttons will do, when you have the winding which is on the cassette like this, when the current player is playing the contents on this position. Suppose in case if I want to skip these two and move towards this particular thing, this action we call it as forward. Suppose if my current pointer is here and I want to rehear the music that exists some locations are before it. Okay, so I have to move back. That's what we call it as rewind operation. So this is the context, and this bidirectional memory unit along with the control unit, which are part of your finite automata, together is what is called as a Turing machine. So what is actually needed, okay, in order to have a complete recognition system? So we need a finite automata along with a two-way accessible memory, which we don't have in your pushdown automata, and together this is called as a Turing machine. So this Turing machine, let's say let's have a look at with an example. So we'll have a tape where initially all the contents will be with blank, and the input pointer will start pointing to the first location. Suppose if I start writing this, let's say I want to type or store a word called hello. Okay, suppose if I type H, yes, this got changed. Then E, I am typing, yes, this got recorded. Then I want to type L, okay, but by mistake I have typed I. Okay, so this is a wrong input, but I haven't recognized that. Then I am moving on to type L. Then after reaching this position, I have understood that I have done a mistake and I need to move to the back to change it. Okay, so this is not possible in pushdown automata, where it is possible in your Turing machine. So what I can do, I can move back, okay, and I can convert this, replace the character with the new character, then skip all the required characters and move towards the last blank symbol, completing the process, right? So that is about your Turing machine. So formally, how to define a Turing machine? Yes, it's a finite automata plus memory unit. So the components of finite automata, states or set of symbols, non-empty input symbols, and start state, okay, set of final states. Then you have a transition function, and then you do have not a bottom stack marker, sorry, you have to have a blank symbol over here. So q sigma delta tau, sorry, q naught f, or the states of finite automata, along with tau, which is nothing but the set of symbols that you can store on the tape, along with blank, the symbol which is used to recognize the emptiness of the state, will be the formal definition of Turing machine. Now, how to represent this? As usual, we have two different ways. One is through transition diagram, second is through the transition table, right? Let me draw one Turing machine, Q naught, Q1. If it is A, replace it with X, move towards right. So that is the configuration. A, replace it with Y, or X, move towards right. Suppose if it is B, replace it with B, move towards left. V, V, move towards left. So this is the configuration. This is the input of the in the tape symbol. Suppose if A is my suppose A is the input symbol. Okay, that is under the current input pointer which is on the tape. Replace it with by X and move towards right. Actually, there are two directions of movement. This is right movement and this is left movement. Okay, either you can use arrow mark or you can use R and L. So this is the content of the tape before transition. This is the content of the tape after transition. So now this is a graphical representation where states Q is equal to Q naught, Q1, Q2, and you have sigma as A, B, and you have tau as X, A, B. So whatever symbols that you can have on the tape that represents tau, and Q naught is the start state, Q2 is the final state, blank as usual B, okay, and delta is the transitions. All the tape symbols will be part of the column. Now from Q naught on B we don't have transition, X also don't transition. From Q1 on A we have transition, yes, on right, and then from Q1 on B it is to B towards left direction and we don't have transition here. Q2 it is star which is the final state and this is the start state. When on A we don't have transition, this is B left, okay. So that is about the transition table. Let's see one simple example of designing a Turing machine with a logical explanation. L is equal to A power n, B power n, where n greater than 0. Let's take one sample value n is equal to 3. So what to do? Assume the tape initially contains all blank symbol now filled with the word that you want to check. So what is that? It is n is equal to 3. So the tape will initially have A followed by B. Okay, after that you will have blank and before that also you will have blank. And your input pointer will point to the first symbol. Now the concept is that whenever I see a on my input, I need to check whether I have an equivalent B. That's the concept. Since both side movement are permissible, no problem at all. You can move in any direction as you want. So initially what can I do? I'll check whether I have an A, I can replace it with X. So I can move towards the right. Just check whether there exists a B after A. So I have checked one A and I'm skipping all A's, and while reaching B, I'll try to convert it into Y. What does it mean? I have seen an equivalent B for an A. Now once seen, I can take a left turn. Again I will skip all A's until I see an X, because X is what is our last conversion. So once I see an X, I'll take a right turn. So till that time I have to move towards left. When I see an X, I have to take a right turn. The second X, I have to change to X. Now when I move towards Now when I start moving towards right, along with A, now that I will see already converted Y's also will be on the input, right? That also we need to skip. And we are expecting an equivalent B now. Yes, Y I will replace, then keep moving towards left until X. So this process continues. Right, when I reach X, take a right turn, convert A, and then move ahead, change B to Y. This process continues, and third A also I'll be changing to X, move towards right. Third B I'll be changing to Y, move towards left. After X, now instead of A I'll have a Y. What does it mean? All A's we have crossed out. So just we need to skip all Y's to check whether no more B's are left out on your input. So when will it happen? When you have a blank symbol. So if there exists a blank symbol, you can take a left turn, stop at this position, because always the input pointer is restricted to this area. So while reaching the final state, it's a good practice to stop at the last character. So and you can say the word is accepted. Otherwise, on either case, if you are left out with more A's or more B's, you can stop or you can enter into a dead state. Now let's draw a Turing machine for this. Initially. So I'll draw the diagram initially. Now let's draw a Turing machine for this. Initially the pointer will point to this location. So we will be in start state Q0, right? So what is seen on the input is A, which I need to convert to X. So I'll be converting A to X, moving towards right. So I'll be moving towards right. Any number of A's that comes on the input needs to be skipped. Skipped means A needs to be replaced as A. Keep on moving towards right until you see a B. So when I reach Q1, whatever A's that come on your input, you have to skip and keep moving towards right. Once it is done, then when I see a B on my input, okay, then I have to convert that to Y. So I am expecting a B to be there on my input, change it to Y. And what is the direction of movement now? I have to take a left turn. So left turn. Okay. Now what are all the symbols I will skip on my way towards the left? It is A. I have to skip, keep moving towards left. So till what time I have to skip? It is when I see a X on my input. I have to, because until I see an X, I don't know how many A's are there on my input. So when I see an X, it means that is the last character which I have changed. And when I reach here, I have to take a right turn, then do the same process. Okay. So what will I do? When X is there, okay, as soon as you are skipping and moving towards the left, when you see an X, leave it as such, move towards right. So I'll be in this position now, right? Since the process needs to be repeated for any number of A's and B's, I'm taking the control to Q0. Now the second A I'll be replacing by X, keep moving towards right. Now that along with A, I'll have y's also in my input stream. So I'm adding y's also for skipping. Yes. Now keep on moving to till you see a B on your input. So this B I'll be changing to Y using this, and then while moving towards left we have to skip. So while moving towards left, now you see what is seen on your input is Y also. So this is the Y we replaced. While moving towards the left, Y also we have to skip along with E's. So Y also we have to skip. So move towards left until you see an X. So this process continues all A's. See, this will also become X, this will also become Y. And finally, when I see and when I reach Q naught, instead of A, I'll be having Y as my input. Okay, so what does it mean? When Y is there, just leave it as it is. Okay, move towards R. So our intention is to check whether B's are over next, because since A is over, we are left out with Y. Okay, so now skip all Y's, keep moving towards right. Finally, what is expected is to have a blank symbol. Okay, move towards left. As I already told you, we have to reach the last location, last character. So we are moving towards left. Here, when the number of A's are more than B's, then what will happen? After replacing A by X, let's say you have 4 A's. First A I'll replace by X, move towards right, replace by Y. Move towards left, X, then Y, and then X, then Y, then now we'll replace this by X, expecting another B. Okay, while moving after B, what will happen? Okay, so after Y, I'll be expecting B, but it won't be there. Rather, you will get an blank symbol. So from here, okay, when you, instead of B, when you see a blank symbol, it means you can enter into a dead state. Okay, that is one way. This represents the fact that number of A's are more. If the number of A's are less and number of B's are more, then in the state Q3 again you will have B instead of blank symbol. So there also you can enter into a dead state. So that's the basic way of arriving at a Turing machine. What are the kind of problems that the Turing machine can solve? Okay, basically all computational devices. If you take any desktop or laptop or any that is a notebook or any computational device, you have arithmetic and logic unit. Logic unit is what we are discussing till now, be it in the part of finite automata, pushdown automata, or Turing machine, wherein the equivalence, the relation between any characters. Let's say if you are writing a equal to b, okay, that's what is the language a power n b power n. A kind of, okay. Similarly, some relational operations are being checked. So that is what we call as checking for patterns. So this is possible with finite automata, pushdown automata, and Turing machine. But along with that, our computational device also has arithmetic unit, which is used to perform all sort of arithmetic operations. So let's say if you are writing C is equal to A plus B, how does this happen? How is it being computed? You are writing A modulo B. How is it being computed? Okay, so that's the way Turing machine has to be understood clearly, because this is not possible with finite automata or PDA, which is used only for pattern matching in general case. Turing machine is actually the base for the computation model, wherein both pattern checking, which is the logical operation, and the arithmetic operations. Okay, so arithmetic unit plus logical unit is possible. Okay, so that's about the introduction to Turing machine.